Hello and welcome back to another exciting discussion about weather radar. And we're pounding our way through the radar equation. If you were motivated enough to get through the previous video or PowerPoint, we started developing an equation, the radar equation, which was getting very complex. Where we left off last time, we started discussing how a target will intercept power coming from radar and how that power is backscattered to the radar. So this is the equation that we had. It's called it's the power that's returned, PR, P sub R actually. And it depends upon what is scattering that radar energy at a distance. In our previous video, we looked at just a kite, and we said that kite had a cross-sectional area, A sub sigma. We're going to modify that a little bit now. We're going to define the area that's scattering the radar energy, that's intercepting and scattering the radar energy back to the radar as the backscatter cross-sectional area. And we're going to use the symbol sigma to define that. And by definition, it's the physical size of the target that's not the same size as it appears to the radar. So we've got this scatter out at a distance, and it's returning radar energy. The equation that you see on this slide is getting kind of complex. Simply what we're going to do is replace the A sub sigma, the area of the scatter, with the sigma. And now we've got to talk a little bit about how the radar wavelengths are scattered by objects in our atmosphere. It depends upon how big the objects are in our atmosphere. Are they size of a dirigible or a blimp, or are they on the order of an aerosol particle or even a cloud droplet? And it depends upon the wavelength of the radar, the wavelength that is intercepting the targets at a distance. So if you have a very large sphere with a diameter d, then we're in the optical scattering range, which means let's assume that we have a basketball or something bigger than the basketball, a beach ball, or for that matter, a bouncy ball, and it's got a large diameter. Our National Weather Service radars operate at 10 centimeters. If the diameter of our target is bigger than 10 times the wavelength, then we're in the optical scattering regime. So that means that our wavelength for the National Weather Service radar is 10 centimeter. Multiply that wavelength by 10, that gives us 100 centimeters. So if the diameter of our object in the atmosphere is bigger than 100 centimeters for a National Weather Service radar, it'll scatter in the optical scattering regime. And that means that our backscatter cross-sectional area, sigma, is simply the area of a circle, which is pi r squared. So that's pretty simple. But it depends upon, once again, the wavelength. Okay, let's try looking at another case. And in this case, we're going to look at targets in our atmosphere that are very, very small. We're talking perhaps maybe aerosols or maybe cloud droplets, very small. In that size range, for National Weather Service radars, they typically scatter in something called the Rayleigh Scattering regime. And what that means is the diameter of those objects are less than 1/10 of the wavelength of the radar. National Weather Service radars, the WSR 88Ds, are 10 centimeter radars. So 1/10 of 10 centimeters is 1 centimeter. So that means that Rayleigh scattering, or the backscattering that we get from these objects in our atmosphere, small objects, are a function of this equation, the backscattering cross-sectional area equation for Rayleigh scattering, which, as you can see there, is kind of complex. You got pi raised to the 5th power. You got this thing called k raised to the 2nd power. D, which is the diameter of the droplets or aerosols or whatever is in the atmosphere out there, that's raised to the 6th power. All that divided by the wavelength of the radar raised to the 4th power. So in our atmosphere, we have things of various sizes, aerosols and hydrometeors. Cloud droplets are typically, on the order of about 10 microns. These are what clouds are made of, just suspended clouds that are not precipitating. These cloud droplets sometimes can go up to maybe 50 microns in diameter. Raindrops, though, are hydrometeors that fall and they hit you and they make you wet. They hit the ground and make the ground wet. Those are typically in the order of anywhere from 100 microns to about 1,000 microns in diameter. So looking at Rayleigh scattering, that means that we typically, with the National Weather Service radars, are looking at raindrops. We're talking, the National Weather Service radars are 10 centimeters, which are 100 millimeters. 1/10 of that would be 10 millimeters, which is about 10,000 microns. And compare that to a typical raindrop. A typical raindrop is usually about 1,000 microns. So in other words, the things that we see in our atmosphere, typically precipitation-sized particles, are what show up on National Weather Service radars, 10 centimeter radars, because that's the wavelength that they selected. That's what they want to look at. They want to look at precipitation-sized particles. Now, things get a little bit crazy when you're in between optical scattering and Rayleigh scattering. Remember, we said optical scattering is for really large objects like dirigibles or beach balls. And then Rayleigh scattering is for really small objects like cloud droplets or even precipitation-sized particles. How about in between? In between, that would be, let's see, somewhere between about 10 millimeters and 1,000 millimeters. And that actually is about the same size as hail. Hail ranges from about 6 millimeters all the way up to about 200 millimeters in diameter. The problem is the equation is not linear. It's not real straightforward. It's kind of complex. And this is what the scattering regimes look like. So on the left-hand side, you can see a very linear scattering regime. That's Rayleigh. And then the optical regime is also linear, but it's pretty straight, but horizontal on this graph. But in between, you got one that kind of oscillates between high, low, high, low, high, low. And that's your Mie scattering, and that's where you find hail. So you can see that hail, there's not a very clear relation between the size of hail and the amount of power that it returns back to the radar. So hail is pretty complex, and you probably know that already. So that's where we're going to end this discussion in this video. And next time we'll continue on with our radar equation, and we'll get even more complex. I hope you enjoyed this.